And good morning. All
Good
right.
morning.
So, what did we talk about last time? Do you remember? Oh, yeah, we were talking about ions and Bohr atoms and all kinds of wild things. Um, Today should be a fun lecture. If I can remember how to do this. I didn't get much sleep last night, so I may be a little bit wackadoodle. There it is. So today we're going to talk about, last time we started talking about the Bohr atom, we talked about ions, we touched on the two different kinds of bondings. Today we're going to talk about periodicity and the periodic chart. And we're going to get at least started on quantum theory. So 19th century, they started discovering and isolating all of these elements. And they took all kinds of measurements. They took melting point, boiling point, reactivity, and figured out the valencies, which was, since this was before electrons were discovered, started figuring out all those properties about different elements. And it was chaos. It was just chaos. Russian dude by the name of Dmitry Mendeleev. Took a whole bunch of post-it notes because post-it notes are much older than we realize. No, he didn't use post-it notes, but he made little cards. And he put different elements and all of their properties, all the elements that he knew, he put their properties down on these little cards. And then started sorting and arranging them according to these properties. And he came to realize that if you arrange, back then they knew the atomic masses of these elements, and he came to realize that if you arrange the cards according to atomic mass, he came up with the law of periodicity. And at a scientific meeting, and by the way, for this lecture, you might want to have your book open in the front leaf so you can take a peek at the periodic chart as we talk. He came up with a periodic chart, the first modern periodic chart. And he introduced it at a scientific meeting. One of my favorite quotes by a scientist, somebody at the meeting, and I wish I knew who, said, "It was as if a veil had been dropped from my eyes." So let's look at the periodic chart. How do I want to do this? Well, for the moment, I'm just going to draw the periodic chart. I now have a tattoo that looks very much like this. The dimensions are always off when I do this, but it'll work. So here we have the periodic chart, and I apologize for being sideways. Now, Dmitry Mendeleev arranged the elements by atomic mass. He was wrong. They should not be arranged by atomic mass. They should be arranged by atomic number. But back then, they didn't know anything about protons. So they didn't know the atomic number. number of these elements. And if you look closely at the periodic chart, you will see some exceptions where suddenly the atomic mass drops rather than increasing. I'm looking for such an example now. Like, for example, iron, cobalt, and nickel. Iron has an atomic mass of 55.85. Cobalt has an atomic mass of 58.93, but nickel has an atomic mass of 58.69. So it drops just a wee bit there. Then it goes to zinc, which is 65.39. Mendeleev noted these differences. He was looking at properties, and he thought atomic mass was how the periodic chart should be arranged. So he did recognize and note the differences where it just seemed like the elements, if you went by atomic mass, just switched. For some reason, they just didn't quite fit correctly. We have periods, columns, the rows are called periods. The name derives from periodicity. The columns are called families. They are called families because a family, which is a column in the periodic chart, all have very similar chemical properties. For example, the very first period, and by the way, hydrogen and helium, well, hydrogen anyway, is very much an exception. Hydrogen is an exception. In fact, some periodic charts will actually also put hydrogen over here. We're going to talk about why that is, but the very first column here are called, and some families have very specific names. So the very first column here with lithium, sodium, potassium, rubidium, and so forth are called the alkali metals. Alkali is another word for basic. You have your acids, you have your bases. So the alkali metal, when you drop an alkali metal in water, it reacts violently. And it forms an alkaline solution or a basic solution. So it's called an alkali metal. How reactive they are with water really depends on where in the family you are. So lithium will fizz around and spark. Sodium will fizz around, spark, and eventually, if you have enough of it, explode. Potassium just explodes. Blam, it's done. And as you go further down that row, the more reactive those metals are. But they all react violently with water. Next to the alkali metals, column 2 are called the alkali earth metals. The alkali earth metals, very similar to the alkali metals. They react with water, but not as violently, not nearly as violent. The very last column on this side these are called the noble gases. My father's gases were nowhere near noble. But these gases are very non-reactive. We call them inert. They do not react. Inert. They do not react. When chemists are trying to do something where oxygen would interfere, because oxygen is so godly reactive, and we'll explain that actually. Well, no, not in this class. People don't stop to think about how reactive oxygen really is. Oxygen has enough energy to keep us alive. It's oxygen reacting with sugar that provides the energy that allows us to live. It's also oxygen that burns down millions of acres of forest every year in forest fires. And I want you to consider this. Air is 20%, a little less actually, than 20% oxygen. The other 80% of air, 80%, are gases that can be used to extinguish flames. They can all be used to extinguish flames. And yet, with 80% fire extinguishing gases, oxygen at just 20% prevails. It's just incredibly reactive. And you'll notice, by the way, whoa, what just happened? Go away, come back. There we go. Different periodic charts label these in different ways. The periodic chart uses, in my book, uses Roman numerals. So column 7A, so there are 7A. This one starts with fluorine up here. These are the halogens. Highly, highly, highly reactive. Very, very deadly. Chlorine. Third one down. Fluorine is just very reactive, very different than the metals, but still extremely reactive. Fluorine, hydrofluoric acid is the only acid strong enough to etch glass. It used to be used to etch glass back in the days when they used to make cars and they put some time into it. They would etch the windows in the back, and they used hydrofluoric acid. Chlorine. Chlorine was used as mustard gas. That was the gas that they would use, heavier than air, to fill the trenches in World War I to kill the enemies. Bromine, a good whiff of bromine will permanently destroy your sense of smell. These are extremely dangerous gases. And by the way, when you mix cleaning agents like ammonia and bleach, chlorine gas can be given off. Was dating a woman in New York City who was talking about how she was going to go home. We actually just split up that day, and she was going to go home and clean. And she said what she does is she takes ammonia and bleach, and she knows it's a good mixture when it starts to bubble. Well, what's bubbling is it's giving off chlorine gas, which is deadly. And I begged her not to do it, and I never heard from her again. I don't know if she survived or not. She wasn't listening to me at that point. column 6A. Here's a name that you're not going to hear very often, but for completeness, we're going to put it down. These are called the chalcogens. The chalcogens. This starts with oxygen at the top. Okay, we're good so far. Any questions?
Nope.
There's a funny little dark line in every periodic chart, including the one on my back, tattoo that I have. Kind of runs diagonally like this. To the left of that diagonal line, we have the metals. Anything to the left of that line are the metals. Metals tend to lose electrons when they form ionic compounds. Tend to lose electrons. That means that to the right, we have the nonmetals. And if metals tend to lose electrons, nonmetals tend to gain electrons. These are generalities. There are always exceptions. You can kind of beat these elements and do all kinds of weird things with them. Between column 2A and column 3A, these are called the transition metals, which we're largely going to leave alone for a while. And here's why. Metals tend to, and down here we have the lanthanides and the actinides. The lanthanides and the actinides belong right here in the transition metals. Why do you suppose, and you may know this, those of you who don't know, my friend Kim is like my best friend in the whole world. And we talk about stuff like this periodically. So let's see how good Kim's memory is. Do you remember why? I explained this to you once. Do you remember why we separate out the lanthanides and the actinides from the main body of the periodic chart?
Nope.
The answer is trivial. It's trivial. The only reason we separate those metals out is so that the periodic chart fits better on an 8.5 by 11 piece of paper. There's a version of the periodic chart called the long form. And it's just really long because those lanthanides and actinides, when you put them where they belong, it just forms this really long, really skinny periodic chart. No, that's wrong. That's still wrong because I just did the exact same thing I did before. There, like this. It's just really long, really skinny, kind of gangly. Nobody would date it. It's very sad. Nobody wants this lanky kind of a thing. So anyway, I do think I'm missing something there, though, but that's okay. You get the idea. If you just split the periodic chart right here and take the lanthanides and actinides and put it here, it's just going to make the periodic chart really long. So anyway, and here's something that you're going to want to remember. I told you that metals tend to lose electrons, with exceptions so rare that I don't even know any. The alkali metals, when they form ionic compounds, always form a charge of +1. Always, always, always. We used sodium chloride as an example before. Sodium is always +1 charge. You're going to want to know that in future chapters when we talk about ionic compounds. The alkali earth metals always, always, always form +2 charges. In the valence shell, as it turns out, the alkali metals all have one single electron. So to fulfill the octet rule, they just lose it. It's gone. It gives them the full octet. The alkali earth metals all have 2 electrons in the outermost shell. So when they form compounds, they're gone. The transition metals, they have all kinds of electrons, at least 3 and usually more. The only other one that you should remember is aluminium. Aluminium, when it forms compounds, always forms with a +3 charge. Actually, I'm going to use a dash line here because this is actually still part of the transition metals. All of the other transition metals have too many electrons to lose in order to get that full octet. So they compromise. They lose a certain number of electrons depending on the compound, and those number of electrons can vary. We're going to talk about how that is. So the transition metals, that's why we're going to skip over it for a moment. The transition metals, sometimes they lose 1 electron, sometimes 2, sometimes 3, as many as 6. They can lose up to 6 electrons. But the more electrons they lose, the less stable they are, because it's something that we call charge density. Charge density. If they lose too many electrons, that charge density becomes unwieldy, it becomes unstable. Those compounds are usually very unstable, highly reactive. On the other side of the periodic chart, the noble gases do not form compounds, so we don't have to worry about the charges that the noble gases, they're always neutral, it's always 0. The halogens, however, always, always, always form a charge of -1. The halogens are all 1 electron away from having a full octet in the valence shell. So they will all gain 1 electron. Anytime you see a halogen, you just know -1 charge. In a compound, remember, in an element, in its elemental state, if you have just chlorine gas, it's still neutral. But in a compound, it always forms a -1 charge. For the most part, we stop there. Oxygen is always, always, always -2. However, the rest of the family can do weird things. So we're not going to assume any particular charge for anything other than oxygen. Always, always, always. Sorry, I hear my cat whining, and I don't want her coming up here and showing off her butt again. Okay. So that's the periodic chart. One of the funniest things, librarians cannot say periodic chart. They can't do it. As far as I can tell, none of them can do it. And the reason is very simple. Through the years to support the library, when I taught every year, I would invite librarians to come over and talk about the resources available to my students in the library. And they always brought up the periodic chart and where you can find the periodic chart and all that kind of stuff. But every time they said it, they always pronounced it periodical chart. What's a periodical? It's a magazine. They deal with periodicals every day. So they're so, it's muscle memory. They're so ingrained with saying periodical. They can't leave the AL off. So it's always a periodical chart when they talk about it, which is, I think it's just adorable. I think it's very sweet. But I always thought that was kind of funny. Okay. When you look at properties, melting point, boiling point, electronegativity, you're going to hear that term a lot. So let's introduce that today. Electronegativity is the pull an element has for an electron. How strongly does an element want an electron? That's what electronegativity is. The more strongly an element wants an electron, the higher the electronegativity. As you might imagine, the metals all want to lose electrons. So you tend to have low electronegativity in the metals. And let's give this a symbol. This is the Greek letter epsilon. Looks like a backwards 3. So we have a low electronegativity to the left, high electronegativity. Again, always ignore the noble gases because they don't want, and they just don't want to play. So aside from the noble gases, nonmetals all have a high electronegativity because they all want to gain an electron. This is what we mean by the law of periodicity. Properties like electronegativity tend to increase, in this particular case, from left to right across the periodic chart, across any given period. On the other hand, on the side here, in the families, if you think about the structure of an atom, you have your inner shell electrons, you have your valence shell electrons on the very outside. As you go down the family, we're adding more and more shells, which means that those atoms are getting bigger, 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 bigger. always increasing in size. As they get bigger and bigger, those valence shell electrons are further and further away from the nucleus. And the nucleus is what is holding the electrons together. It's electromagnetic. You have a positive nucleus. Yes, not positive one. I mean, you get up to francium and it's a charge of positive 87 because it has 87 protons. So the size of that positive charge is increasing, but nonetheless, the electron is getting farther and farther away. As the electrons get farther and farther away, they're held on more and more weakly. It's easier and easier to just knock that one electron off, which is why, by the way, the alkali metals, the reactivity increases as you go down the periodic chart. Down that family, that one electron is being held on more and more loosely, which makes it much more easy to take it away. Therefore, our electronegativity increases as you go from the bottom to the top. This is true in all family. Rubidium down here is the most reactive metal on the periodic chart. This is the most reactive right here. It is the one that most wants to lose that electron. It will do anything that it can to get rid of that extra electron. Fluorine, on the other side, is the most reactive nonmetal. Because fluorine has the highest electronegativity, it is the one that wants the electron the most. It only needs one more. It is so close to having what it wants. So if you were to put a diagonal here, electronegativity increases this way. And there are other properties as well that I could talk about, but I'm not going to because I don't think they're terribly important. Important. Why is it so hard to say that first T in the word important? And you sound weird when you say it. It's important. It is important. Anyway, electronegativity is so very important. The rest of them, we talk about things like atomic radius, melting points, boiling points, and you'll find that, yes, you have a general trend on so many of these things. So they might be increasing, and then there's going to be a funny dip somewhere, and it's going to continue increasing. Or it might be decreasing, and then there's a funny increase. These are due to electronic effects that we're going to talk about very, very soon. I've been running late with our breaks. I think today we're at a good stopping point. So let's take a 6-minute break. I'm not going to say how many minutes. Let's take a quick break. We will come back at 10:40, please. Does that work for everybody?
Good.
All right. Okay, we are recording. So what is up with the periodic chart? What is up with why elements lose or gain the number of electrons they do? What is up with the exceptions to the trends? It's one thing to recognize exceptions and trends and things like that. It's another thing to understand them. We're going to dive into one of my favorite topics now, quantum theory. Quantum theory is something that very few people understand. It seems to be, it has a lot of draw. People love the concept of quantum theory because it feels like anything is possible in the quantum realm. And it really is. It's just there are bizarre things. And they don't make sense to us. They will never make sense to us. Don't try to understand quantum theory because we cannot. We live in a classical world. We are classical beasts. We follow classical thermodynamics. And classical thermodynamics tells us that we are allowed to know position, and momentum as exactly as we want anytime. We're allowed to know that. And we use this every time. We use it every day. If you're going to catch a ball, if you were out playing with your grandchildren, which I know nobody does because grandchildren are terrible creatures. But if you're out playing ball with your grandchild and your grandchild throws a ball and you want to catch it, when they're very young, they don't have a lot of control. So that ball could go anywhere. And what do? You do a calculation in your head. You don't use numbers. You don't use math. But you do this calculation in your head. You know where the ball is, where it's starting, and you know where it's going. Now, as you recall, these funny little arrows tells us it's a vector, which means it has direction and magnitude. It is to say, you not only know how fast it's going, you also know where it's going. Okay? If it's not a vector, then it is a scalar, which means all you have is magnitude. Magnitude. If I'm telling you I'm driving 70 miles an hour, when will I arrive? Well, you have no idea. You don't even know where I'm going. I'm driving 70 miles an hour, but in what direction? I'm not giving you a direction. That's speed. That's a scalar. You know how big, but you don't know direction. A vector is both direction. I'm driving north at 70 miles per hour. It's direction and magnitude. Momentum, by the way, is both a scalar and a vector. Momentum is mass times velocity, which has speed and direction. Okay, with me so far? By the way, I'm going to throw a lot of equations, a lot of names at you. I'm not going to ask you to memorize or do any of this math. The reason I'm doing this is because I'm going to we cannot understand quantum mechanics, but we can learn the lessons that it's teaching us. And it's going to teach us the lessons. Oh, I'm not sharing my screen. Thank you for pointing out that I'm not sharing my screen. You're absolutely correct. I was so enamored with myself and looking at myself. Okay. There you go. Where was I? Okay, so we can learn the lessons of quantum mechanics, and the lessons of quantum mechanics is going to tell us about electrons, which in order to understand chemistry, we have to understand the electrons. But we can never really understand the way electrons behave. We're not allowed to, and I'll talk about that in just a minute here. But when we go to catch that ball, we know where the ball is originating, and as soon as it's moving, we can see the direction it's going. So we do that calculation in our head. Where do I have to be to catch that ball? And we go there and we catch it, and our grandchildren are awed by us. How the hell would I know? I don't have children, let alone grandchildren. But anyway, we do that calculation in our head of mass, of position, and momentum. In quantum theory, sometimes it's called quantum mechanics, sometimes it's called quantum theory. All means the same thing. As it turns out, it is illegal for us to know position and momentum simultaneously. It's illegal. So we can see the child throw the ball and the ball suddenly disappears in some direction that we cannot ascertain. Or we know where the ball is heading, but we have no idea where it is at the moment. That's quantum theory. You're not allowed to know position and momentum simultaneously. That's why in the quantum world, classical physics breaks down. If we had a quantum friend here, quanta, they would think that our world is just as strange as we think theirs is. We do things that are absolutely impossible, like knowing position and momentum simultaneously. We're not allowed to know that. I'm going to throw a lot of math. I'm going to throw a lot of names at you. And the reason I'm going to throw the math at you is not because I expect you to be able to do it on homework or on one of our myriad of exams or quizzes that we have in this class, because I know you hate those quizzes. The only pop quizzes we have are tarts. Anyway, it was like a joke. It's just smaller. I want to do this because I want you to understand. Once we get to these rules, they're going to sound arbitrary, but they are not. Those rules come about because of mathematical formulations. They are results of mathematical equations. They're not going to look like results of mathematical equations because letters have been assigned. So we're going to use the letter S at one point, and that actually represents the number 0. The letter P is going to represent the number 1, and so forth. So we're going to assign letters to these things, so it's not going to feel mathematical, but it is. And I want you to understand that. And what the math tells us is so bizarre, so strange, so out in left field, it cannot possibly be true. There are physicists today. I'll drop a name here. I was a visiting scientist at Harvard. No, I didn't study at Harvard, but they invited me to come and work with them. Working with the greatest guy in the world, Nobel laureate. Great guy. Very nice. Whose name eludes me at the moment. I'm a little ashamed of that. Too much Diet Coke, I guess. But I went to a seminar. They had invited a physicist to come out, and his whole research was to disprove quantum theory. And he could do it. He could reproduce everything quantum theory predicts using Newtonian or classical physics. Newtonian is another word from Isaac Newton, Newtonian physics. Isaac Newton was famous when he was hit in the head with an apple what he was most famous for saying was "son of a damn." Anyway, the way he had to do it, though, was by throwing arbitrary constants into the equations. And scientists don't like arbitrary constants. So if you cannot justify a constant, we don't believe it. But here's how bizarre quantum theory is. It makes so many weird predictions, like Schrodinger's cat. Most people talk about Schrodinger's cat, and they have sort of a vague idea of what it really means. You put a cat in a box. My cat is locked out of my room. Is my cat alive or dead? Well, we hope she's alive. She's a sweet cat. But we don't know. We honestly don't know until we actually open the door and look. Unless she sticks her little paw under my door, which she's not doing at the moment. Until we actually open and look for her, we don't know if she's alive or dead. She could be dead right now, for all I know. And Schrodinger's cat says, until you actually open that door and look, it is neither alive nor dead. It is actually both alive and dead simultaneously at the same time. There is something we're going to talk about called spin. Highly misunderstood. Even textbook authors do not understand spin, and there's so much confusion. We're going to talk about why textbook authors are wrong. We'll get to that. But spin can be either spin up or spin down. It's the nature of an electron. Electrons are either spin up or spin down. Which are they? Well, until we measure it, they're both at the same time. So here's an experiment that they did. They took a beryllium atom with 4 electrons, and they shot it with not 1, not 2, but 3 lasers. Very highly tuned energy lasers. That's the beauty of lasers, is you can tune the amount of energy in them. And it's very, very compact. The first laser, remember h nu is our symbol for wavelength. The first laser knocked off 1 electron to form the beryllium ion. Now it's charged. And they isolated the beryllium ion, that's boron, beryllium is Be, boron is B. They isolated the beryllium ion in a vacuum, very, very high vacuum in a magnetic field. Because it's charged, they could isolate it in space. So you put the proper positive charge on the bottom plate, negative charge on the top one. If you mess it up, it's going to go all the way up and hit that plate. But if you do it just right, tune it just right, you're going to have that beryllium atom floating in space in a vacuum. They hit it with the second laser. Which excited the spin up electron only. Now we're talking about 1 electron. 1 electron can be spin up or spin down, but until we measure it, it's both at the same time, which means they can excite just one of the 2 states, either spin up or spin down. I'm going to denote the spin up as a star there. Actually, I'm going to go star spin up. Now you have a beryllium atom with 1 electron, just 1 electron in the valence shell, and now that electron is both spin up in the excited state and spin down in the ground state at the same time. That's when they hit it with the third laser. And here's what happened. They moved the excited state beryllium away from the ground state beryllium. Okay, with me? And what they did was they separated the two berylliums. They did not split the beryllium. It lasted for a very, very brief period of time, but they did not split the beryllium. It was one beryllium atom, but it existed simultaneously in two different locations at the exact same time. It's like a happy you and a sad you standing 10 feet apart from each other, looking at yourself. Is that possible? In our realm? Oh, hell no.
No.
No. But in the quantum realm, and this experiment, by the way, very sophisticated experiment, it proved Schrodinger's cat. It proved it. The beryllium atoms were about 10 times their radius from each other. One single atom existing in two different states in two different locations at the same time. Impossible in our world, but in quantum theory, not only possible, but proven. This is why most scientists believe in quantum theory. That's why it's a theory and not a hypothesis. I mean, it started out as quantum hypothesis. But everything that quantum theory can predict and be tested, everything it can predict that can be tested, it has been tested. And we have found no exceptions. It has always proven to be absolutely correct every single time. And it doesn't matter how bizarre those predictions are, like this one. They still have been proven true. So what is quantum theory? Well, first of all, why can't we know position and momentum simultaneously? Dude by the name of Heisenberg. One word and not two. Most famous physicist, well, not most famous physicist, but a very famous physicist. And he was very famous for saying one thing. I don't know. That's it. Heisenberg. I don't know. Oh, we call it something a little more sophisticated than I don't know. It's called the Heisenberg uncertainty principle. And he did if you have a light source, set it through a series of, oh, what are these called?
Lenses?
Lenses. You have a nice narrow beam. And then you put it through a single slit. Can be anything. You can do this at home. You can actually do this at home. Get a source of bright light, take a piece of paper and put a pinhole in it. And in a dark room, shine the light through the pinhole at the wall. And you're going to see a diffraction pattern. You're going to see not just one spot of light. You're going to see a whole series of light spots. Do this. It's a lot of fun. And they shined it on a wall. And they came up with the diffraction pattern. A series of light and dark spots on the wall. And Schroedinger used basically a geometrical argument and managed to demonstrate mathematically. And he was looking at the main bright spot and the next one over, and he drew a little triangle and used geometry, and he proved mathematically that there is a limit to our knowledge. If you take position and momentum, and you measure this position and momentum as accurately as you want, you can get the best instrumentation that doesn't even exist yet as perfectly as you want. There's always going to be a small error. Okay? If you take a ruler and you measure, I'm not going to say what I'm thinking. If you take a ruler and measure the length of this stylus, there's going to be a small error in it. You take a laser, some sort of laser device to measure the length of this stylus, it too is going to have some small error. Remember our talk about significant figures? We might be able to measure this to 0.000001 centimeter, but there's always going to be that number stops. There's always going to be a small amount of error in that last digit. So we're going to call that error delta. We're going to have a small amount of error, and we can make it as small as we want because we're allowed to use the best instrumentation ever created in the future to make it as small as we want. Heisenberg proved through his arguments here that if you take the error in position in any measurement and multiply it by the error in momentum, okay, this will always be greater than or less than h bar. The best we can do is h bar. H bar is h divided by 2 pi, where h is Planck's constant, a very well-known constant. If you use radars and lasers and all kinds of crazy gadgets to measure where that ball is that your grandchild threw, where it is exactly and where it's heading, your error will always be h bar or greater. It is the best we're allowed to know. We are not allowed to know it any better than that. So why is it that we can catch that ball? I mean, you know, there's always this error in it. It doesn't matter if we're talking quantum or classical. There's always going to be that error. So why is it? I'm looking this up just to make sure that I'm correct. And I'm not seeing it. Well, the reason we can't see it is because Planck's constant if I'm remembering correctly. Look this up if you're really curious. Planck's constant is on the order of 6 times 10 to the negative 34. That means there are 34 zeros before the 6. And you divide that by another 2 pi. This is so extremely small. Who cares? This will never affect classical Newtonian physics because it is so deadly small. Kim, just a heads up, I'm going to ask you to name somebody famous, somebody alive. But this is so small that in the classical world, we are never going to be affected by this small error. The problem is, in the quantum world, if we are looking at something as small as an electron, this error is huge. We are not allowed to know position and momentum at the same time. Very clever physicists have tried to beat Heisenberg. They did 2 experiments at the same, well, he set up 2 different experiments. The first experiment, they had an electron passing through the first experiment, and that experiment was designed to measure the position very, very finely with extremely small error. The second experiment was designed to measure the momentum of that exact same electron. Well, if you have 2 separate experiments, first experiment's not measuring momentum. We can get that error as small as we want. The second experiment is not measuring position. We can get that error as small as we want. And they made them so small that it would violate Heisenberg's uncertainty principle. You know what happened? They lost the damn electron. They simply, Heisenberg said, nope, I don't care. It's the same electron. You're not allowed to know. There are people who believe that basically Heisenberg is proof that subatomic particles have a form of intellect. I think that's a bit extreme. It's fun to think about, though. So we're not allowed. Heisenberg, it's somewhere, it's doing something, we don't know what. Very important to remember, Heisenberg says we are not allowed to know what that electron is doing. Now, Kim, if you wanted to meet someone famous, someone alive, who would you want to meet?
Someone that's alive.
Someone that's alive.
Tom Hanks.
Tom Hanks. Is Tom Hanks in your house?
No.
Oh, he's not? Shoot. Okay. Well, how are we going to meet Tom Hanks? Let me ask you this. Does Tom Hanks live in your town?
No.
No. Do you know where Tom Hanks lives?
No.
No. Let me ask you this then. If you wanted to meet Tom Hanks and you went somewhere where you feel like you would have the highest probability of meeting Tom Hanks, where would you go?
LA.
LA. Now, we're not talking about where Tom Hanks is exactly. We're thinking about where he most likely is to be found. Is Tom Hanks in LA?
Maybe.
Heisenberg says, meh, we don't know.
Yeah.
He might be there, he might not. We're not talking about exacts. We don't know. It's the most likely place he will be. And now Tom Hanks is part of this entire lecture and will be for all time. How weird is that? He doesn't even know. Along comes a second dude called Schroedinger. Actually, that's wrong. Oh, there's a couple different ways you can spell Schrodinger. This is probably the most common. The correct way is to use an umlaut over the O. An umlaut. And Schrodinger said, okay, you know what? We are not allowed. Heisenberg says so. We're not allowed to know what the electron is doing or where it's at exactly. So instead of working with exactness, like we do in classical or Newtonian physics, let's work with probability. Let's ignore what the electron is actually doing, because we're not allowed to know anyway. We're not allowed to know. Where is the electron most likely to be found? Well, if you go back to this, and like I say, you can do this experiment at home. And I recommend you do. It is so cool. It is so much fun. But when you get a diffraction pattern, that shows that the electrons, they're not operating as particles. They're as much waves as they are particles. They are so small and moving so fast. Let's throw this name in here, that according to de Broglie related the mass of a particle and the velocity of a particle to basically what he did was he demonstrated everything in motion has a certain amount of wave-like behavior. When you are driving at 70 miles per hour, you have a certain amount of wave-like behavior. Well, it turns out that you were so massive that wave behavior is negligible. You're never going to see it. It's like Heisenberg's. It's like H bar. But when you get to be so small as an electron and moving so fast, I don't know. Is it a particle or is it a wave? It might be more wave than it is particle. We honestly don't know. It's both and neither at the same time. It's quantum, man. We can't understand it. So we have some wave behavior and we have some particle behavior. So Schrodinger went to, sometimes, by the way, quantum theory is also called wave mechanics. And the reason it's called wave mechanics is because Schrodinger said, all right, you know what? Let's treat it like a wave. And he went to fluid dynamicists and he looked at their wave equations. And based on those wave equations, he wrote this little gem. H hat psi is equal to E psi. This is Schrodinger's equation. Schrodinger's equation. H hat is called the Hamiltonian. Like I say, I'm not expecting you to memorize all of this. I'm just presenting it so you understand that this is a mathematical formulation. The Hamiltonian. The Hamiltonian is a mathematical formulation that involves both potential and kinetic energy. Potential and kinetic energy. Those are the only two forms of energy that there are. The only kind of energy that exists is potential and kinetic. Potential is the energy that's stored. Kinetic energy is the energy of motion. stored energy versus energy of motion. Things are either stored or they're in motion. There's nothing else. So if you add potential and kinetic energy, you have total energy. You have total energy. Psi is a Greek letter called the wave function. The wave function. What is the wave function? We don't know. The wave function is any function. And we have no idea what the meaning of the function is. It is any function that makes Schrodinger's equation true. It can be anything that makes Schrodinger's equation true. Now, it looks like it should be a pretty trivial solution. You cancel out the psi and you have the Hamiltonian equals total energy. Well, it does. That's fair. But the hat here tells us that the Hamiltonian is an operator. An operator, excuse me, sorry about that. An operator is a function that changes. What it means is that the Hamiltonian, as it operates on the wave function, is changing the wave function. It's changing it while it's occurring. If we try to solve this, that wave function changes. E is just a constant. 7, we don't know what E is. So the Hamiltonian tells us, Schrodinger's equation tells us that whatever the wave function is, it has to be a function. So that as the Hamiltonian is changing it, we come back with the exact same function times a constant. That's what makes this so complicated. And it is so complicated, in fact, that it has only been solved exactly one system: hydrogen. Proton, an electron, no external fields. It has never been solved for anything else. Everything in quantum theory are approximations to the solution of Schrodinger's equation, but they are mathematical formulations. So what does this give us? Well, first of all, we can calculate the total energy. Okay, fine. What else? Well, as it turns out, if you take the wave function, that funny little star means it's the complex conjugate, but for all intents and purposes, it's basically, I'm going to put a little thing here, a funny little squiggly line there means approximately. If you square the wave function, you get the probability of finding the electron. And that's all we're shooting for, just the probability of finding the electron. And that's what psi squared gives us. So now we have a mathematical formulation to find the probability of locating that electron, not predicting what the electron is doing, just the probability of finding the electron. And that's our time today. We're going to pick it up from here on Tuesday. Are there any questions before we break? All right. Don't let this confuse you. Don't let it scare you. Like I say, I'm presenting it so you know this is a mathematical formulation. We're not going to actually do these calculations. Have a great evening.
Bye.